So I'd like to thank the Office of the President. I'd like to thank the professional associates. I think it's appropriate to single out Dr. Rotman, who really played a large role in organizing this event. So we can give him a round of applause. He's patting himself on the back. Now he's getting more kudos. I want to thank all of you for being here as well, though. If you follow the news, you could see headlines in the national news and the world news in relation to climate change that make hosting a climate change symposium important. And I'm proud that Fort Lewis College and the professional associates were willing to do it. Just for example, if I've got a laundry list of headlines, but I won't read them all to you. Just to give you a flavor, EPA scrubs a climate website of climate change. That was a headline from last month. EPA website removes climate science site from public view after 2 decades. That was from April of this year. Some of you may have heard last month that the EPA disallowed some scientists to speak at a conference because their presentations were going to be in relation to climate change. And then I'm sure a lot of you watch the White House Budget Director press briefings on a regular basis. If you happen to watch one in March, you would have seen Mick Mulvaney call climate change research a waste of U.S. taxpayer dollars. And so it makes me happy to know that I work at an institution that takes climate change seriously, work with a president that takes climate change seriously, work with a group of professional associates that take climate change seriously, and work in a community where people would come out to hear about climate change. So for that, I thank you. And again, I welcome you. This is going to be a great afternoon of talks and panel discussion. Welcome to campus, and enjoy the rest of the day.
All right, so here we go. Lifelong Learning Program. We have a lecture every Thursday night during the semester. There are some programs over on the table. It's a free lecture series. The lectures last about an hour with another half hour for discussion on a broad range of subjects. And it's always been a concern that people felt that in an hour you don't go in enough depth about anything. So they said, you know, you've got to find a way to do things a little bit more deeply. So we've a long time thought about doing a symposium like this, and it just takes a lot of energy to pull it together. And for the first topic, we decided we would do climate change, and evidently that was a good idea. You people seem to be interested, and I thank you very much for coming. We understand there's a group of people that came from Pagosa. We understand there's some students that have come from Cortez. We really appreciate all of you folks. Our first speaker came all the way down from Boulder just to see this show, and I'll introduce him in a moment. The Lifelong Learning is a free lecture series, so this is part of that. It's a free lecture series, but it's not free. And so we have this brown box over here, and we ask for contributions. If you can make a contribution, we thank you. If you can't make a contribution, we still thank you for your presence and for attending and sharing this with us. I again want to thank the President's Office. Dean Thomas has been very supportive from day one on this. She supports us by helping us financially pull this off. And she's just out of town today, or otherwise she would have been here. And I thank her. Elizabeth Boussian, who's the Director of Engagement and Annual Giving, she has an office on campus. She has been most supportive, keeps encouraging me and saying, yeah, we can do this. But she has Bill Grimes, an artist in her group, who has done the poster and a lot of the advertising, and Ken Wright as well has helped, and I thank them very much. Rachel Landis is the Director of the Environmental Center. She also could not be here today, but Barry Poole is here. And to that end, there's 2 tables that are in the back room. One is by the Environmental Center. These are tables where you can pick up information. The other one is by the CCL, the Citizens Climate Lobby, and they have information there. These 2 groups together are going to put on a movie on December 1st, and this is just a little ad for that. The movie is called Chasing Coral, and it'll be shown on the big screen down in the Vicedo room. The Vicedo room doesn't hold this many people, so tickets will be quite limited, and you're encouraged to get those, and I'm assuming they will have those there, and they can tell you more about that program. It includes a dinner. You understand this does not include a dinner. Okay. Let's see. I'll just make a few introductory remarks, and then I'll introduce our first speaker. Everybody had ideas about what a climate symposium should be about, what the topic should be, what we would talk about. Should we do politics? Should we do this and the other thing? Well, I feel that we're at a college, and a college or a university, their primary product is knowledge, knowledge and understanding. And so that's what I feel this first one is to that end. You imagine this as a classroom, so you've come here this afternoon to learn more about our climate system. Whether you're a novice at this or whether you've spent your whole life as a climate scientist, I think you will leave this afternoon having learned something. We have these programs. The times on here, this is like speed limit signs. It's just a suggestion. I would like to really move ahead this afternoon because the last part of this is this panel discussion where we will have all the speakers here. Our mayor, Dick White, will moderate it, but that's when you ask questions and you make comments and you really get to participate in this. In the meantime, though, while the lectures are going on, because we're trying to stay on schedule, I ask that you not come forward with leading questions, things that'll send us off in a tangent. If there's something you don't understand that the speaker said that's on the view graph, please ask for a clarification of that. But we save our discussion and questions to the end. So having said that, I will now introduce our first speaker. So did you have a question?
Yeah. How much are campus parking tickets?
Our first speaker will address that, I'm sure. No, I don't know if this is a secret, but if it's your first time, I understand you would get a warning. And if it's your second time, shame on you or something. But that is a number one complaint we probably received, is that parking is not easy here on campus, and everybody in town knows that. But I defy you to tell me of a university you can go to and drive on campus and park next to the student union. It just doesn't happen. And so we had no way of getting, free passes or whatever. There are passes that you can get. But anyway, enough on parking. That's difficult. So anyway, back in the spring when we got going on this, I wanted to get a true climate scientist to give the keynote speech, so to speak. And I knew Kevin Trenberth, a colleague in Boulder, truly outstanding. And so I thought out of the whim, I'll call Kevin and see if he will bite for this. And indeed he did. And he's been most gracious all the way from that time up to coming in this morning on a very early morning flight to come down here and spend a day with us. And I appreciate that. So they're bringing in more chairs, and I think that this is all the chairs that the college has, so stay with it. Dr. Trenberth hails from New Zealand, and New Zealand paid for his tuition at MIT, or his attending MIT, to receive his Doctor of Science in Meteorology from MIT. He was the lead author on the 95, 2001, and 2007 Scientific Assessment of Climate Change. These are the reports of the IPCC, the Intergovernmental Panel on Climate Change. The 2007 group received the Nobel Prize, so to some extent, or not to some extent, Kevin is a recipient of that. He has served on many joint scientific committees, the World Climate Research Program, and so on and so forth, both national and international. There are large scientific societies in the United States and in all countries. The American Geophysical Union is one of the largest for geophysical people, American Association for the Advancement of Science. But all of these organizations give out a very, very few select people. They make fellows of the organization. And Kevin is a fellow of the American Geophysical Union, the American Meteorological Society, the American Association for the Advancement of Science, and he's also an honorary fellow of the Royal Society of New Zealand. So that's quite spectacular, I think. He's received many, many awards. The most recent, which was just announced, is the Roger Revelle Award. This is an AGU award. And this is a union-wide award that will be presented, I assume, soon. This is given for outstanding contributions in atmospheric sciences, in atmospheric ocean coupling, and atmospheric land coupling. These are all the parts of the climate system. So this is really an award, I believe, for climate studies. He has over 500 scientific publications, most of those in reviewed, refereed journals. I could go on and on. He is approaching 70,000 citations. And for those of you that aren't scientists, this is how you do your work. You publish papers in refereed journals, and that's what Dr. Trenberth does. But then people cite those papers in their work. And to have 70,000 is truly amazing. And I don't think we can do any better to have a keynote speaker here today than Kevin. Now, I think I didn't mention the very important thing. He hails from NCAR, the National Center for Atmospheric Research in Boulder. That was the first thing that I was supposed to say. And there he's a distinguished senior scientist. So, Kevin, it's all yours.
Testing, yes. Thank you very much, Gary. And of course, Gary comes from the National Center for Atmospheric Research in Boulder. So he is enjoying his retirement here in Durango. I'm assuming something's on the screen. I can't see it from here.
No food or drinks.
No. How do we get?
The model of the college.
There we go. All right. This is why it's good to have one of these so I can actually see what's being projected. So I'm going to talk about the science of climate change. That's what Gary asked me to talk about. In some of the talks that I give, I get a little bit more into what do we do about it and some of the politics of climate change. And I'll touch on that a little bit, but I'm assuming some of the following speakers will talk about some of the impacts and the consequences and the whole issue of what we do about it, the politics of climate change, which is, of course, very contentious at the moment, will come up maybe in the discussion. I have a number of slides I could pull up if necessary. So firstly, if we're the planet and we want to go to the doctor to say that I'm running a temperature, I have a fever, and there are some symptoms such as the composition of the atmosphere is changing. Carbon dioxide is increasing in the atmosphere. The diagnosis is that these two things are related to one another. And in fact, the human activities are causal because they're responsible for the increases in carbon dioxide. And so the prognosis is for more warming at rates that can be disruptive. And I want to emphasize this disruptive aspect of it. And these will cause strife. And then the treatment is, these have special meaning. Mitigation internationally, mitigation which means reducing emissions. And the second one is adaptation, which really means planning for the consequences. And so that's the treatment. And what we will find as we go into this talk is that we're certainly not doing enough of either of these two things. So my overall comment with regard to the role of scientists in dealing with this issue is that, well, climate change is happening. It's due to humans, and 97% of scientists agree. I won't say anything about the other 3%. I mean, there's religious and various other reasons for that. As a whole, the data are of mixed quality and length. If you were to look at one little piece of it, you might be skeptical that climate change is happening. But when you put it all together, there's no doubt whatsoever that this is happening. And what I'm going to describe to you today is how a lot of these things relate to one another and talk about a number of things that you may not have thought is a part of global climate change, and in particular the global warming aspects. But what we do about this problem indeed involves value systems and politics. And these are often contentious, but there are some ways which you can talk about these things, I think, and hopefully make progress. So, what's causing the warming? We are. The emissions of carbon dioxide comes from industry and electricity and cars and airplanes. And this is the record that was established originally by Dave Keeling, who was a friend of mine from Scripps, and starts in 1958. And firstly, he saw the annual cycle, the breathing in and the breathing out of the planet as photosynthesis occurs and the drawdown of carbon dioxide in the atmosphere in the spring and in the summer. And then the decay of leaves on the forest floor puts carbon dioxide back into the atmosphere in the fall and in the winter. But you can see that fairly large magnitude fluctuation, the annual cycle, is actually dwarfed by the overall trends, the upward trends that are occurring at Mauna Loa. And I want to point out some particular things about the upward trends. This is what the rate was in the 1960s, and then it is increasing and increasing and continues to increase. And last year, the increase was the biggest of any year on record, in spite of all of the efforts that have been made with regard to things like the Kyoto Protocol and so on. This is not going in the right direction. The whole point of some of the international agreements like the Paris Agreement and the Kyoto Protocol is to bend this curve down in the other direction. Carbon dioxide has a long lifetime, over 100 years, and so if we keep emitting into the atmosphere, it accumulates, and this is the consequence. And so what does that do in terms of global mean temperature? Well, there's a lot of fluctuations from year to year in global mean temperatures. Some of these are related to the El Nino phenomenon, and this is the best estimate as to what this looks like going back to about 1880. We don't have records in Antarctica prior to 1958, and so as you go further back in time, it's a bit more ragged, probably because of missing data and the data quality issues as you go back in time. I've estimated on there the pre-industrial value, so this is prior to, say, about 1800, but prior to 1900 doesn't make very much difference. So that's what that dotted line is on there. There's a value for you in degrees Fahrenheit. The increase 2016 is the warmest year on record, 1.7 degrees Fahrenheit above the 20th century average, if you prefer Fahrenheit. And then this is the annual values of carbon dioxide. So now the sawtooth character has been taken out of it. And prior to 1958, the values have been estimated from bubbles of air that have been trapped in Greenland and Antarctica ice cores. And so also on here, I've put the pre-industrial value. The pre-industrial value was 280 parts per million by volume. This is the scale in orange on the right. And again, the 20th century average is what is the zero value on here. And you can see in recent times, we're up over 400 parts per million by volume. And so there's been over a 40% increase in carbon dioxide in the atmosphere over this period of time. And I put these two curves together to suggest that there's a relationship between them. Because we think at NCAR that we can prove that there is, and to do that we actually have to use climate models as well. The warmest 12 months on record is actually September of 2015 to August 2016, up here at about 1.1 degrees Fahrenheit, degrees Celsius, sorry, above the pre-industrial level. The warmth of the 2015 and 2016 years was in part a consequence of the big El Nino event that occurred in the tropical Pacific and has impacts around the world. And some of the biggest peaks in here occur just following an El Nino year. So this dotted line I've just put on here shows you about the halfway point. This is the halfway point for carbon dioxide And so half of the increases in carbon dioxide have occurred since about 1985. 1985. It should give you pause. Yes, sir. I'm sorry, I can't hear you. Well, the shape of this, the character of this curve relates to, indeed, what we call the forcings, the stuff that goes into the atmosphere, which includes the greenhouse gases that are relatively long-lived, and aerosols play some role. So things like the Clean Air Act in the 1970s helped to clean up the atmosphere and remove some of the cooling effects of aerosols. But also, so does natural variability, the interactions with the oceans. And a key part of this actually relates, as much as anything, to decadal changes in something like the El Nino phenomenon in the tropical Pacific. We can talk about that maybe a little bit more later. I put this slide in. Gary was sort of suggesting me I should put this slide. This is one of my slides, which is highly cited, where we put together the overall energy flows through the climate system. This is a two-dimensional view, giving the global values at the top of the atmosphere and at the surface. And I show this mainly to highlight a couple of different things here. At the top of the atmosphere, we have the incoming radiation from the sun, and then we have the reflected amount and the outgoing long-wave radiation. This is the planet radiating heat back to space. And under an equilibrium climate, these values balance one another. But you add these up, and I've given them to the nearest decimal point, because when you add them up, there's an imbalance, which is 0.9 watts per square meter. Well, there's a lot of square meters over the surface of the Earth, but this is equivalent to about 2.5 Christmas tree light bulbs every square meter over the entire surface of the Earth. And it's actually a considerable amount of energy, a lot more energy than we generate using electricity at any time in the US, for instance. So the sun dominates everything that's going on here, and the question is, what's happening to the greenhouse gases which are blocking the radiation from going back into space? And so this has some consequences. With global warming, we have this energy imbalance, and the question is, where does that heat go? Well, I've already showed you one curve showing the global mean temperature is increasing, and most people associate that with the warming of the planet, but it actually does a lot more. It warms the land and the atmosphere. It contributes to the heat storage in the ocean. It warms the oceans, and that means the ocean expands, which contributes to sea level rise. It melts land ice, glaciers, Greenland, which puts more water into the ocean, which also raises sea level. It melts sea ice and warms the melted water. I separated that out because that doesn't contribute to sea level rise, because the sea ice is already floating. And the tricky part, one which I spent a lot of my time on, is it evaporates moisture, which goes into rainstorms. It changes the cloudiness of the planet, which therefore changes the reflection of the planet. How much radiation comes in from the sun gets reflected back to space. Now, there's a lot of these kind of fluctuations that occur somewhat randomly through weather, but it turns out they tend to balance out from one week to the next. So if you have a fine sunny spell and more radiation comes in, there's a rainy spell and more clouds and less radiation coming in, and it's amazing how to see how well those actually balance out with one another. But we have to take this into account, and what I'm going to talk to you a little bit about is some of the consequences of this in terms of rainstorms and precipitation and snowpack, things that matter to us here in Colorado in particular. But overall, 90% of this extra energy goes into the oceans. That's where the storage occurs. And so on an instantaneous basis, this is not very large, but it accumulates over time and it builds up in the ocean. And that's the memory of the past climate change. And those changes are large enough now that they really matter, because they've changed the environment above the oceans. The atmosphere is warmer and moister than it used to be. And this has consequences for things like hurricanes, which we'll talk about later. So what happens if you have extra heat? Well, in the first place, for you guys out here, the human body, the first thing that happens is you sweat, and perspiration and the evaporation of perspiration acts to control the temperature of your body quite well. In fact, if you go to see the doctor and you're running a fever, that's an indication that your body isn't quite working the way it's supposed to. And it's remarkable how well this works. And this works, of course, quite well, but if you don't have adequate water, you can't sweat. You can't keep the body cool. So this is a consequence if you go hiking in the mountains without a water bottle, and you can end up with heat stroke. In not that much time, it turns out, because of the inability to sweat and keep your body cool. And out here in the West, we can use this principle that evaporation keeps you cooler through evaporative coolers, so-called swamp coolers, instead of air conditioners. And it works quite well because of the relatively dry environment we have. And of course, this works also for the planet Earth, because 70% of the planet Earth is the oceans. And so the extra heat, or the heat, goes into evaporating moisture rather than raising temperature. But this is important because, we're evaporating moisture. Where does that moisture go? Well, it gets caught up in clouds and rainstorms and hurricanes, and then it rains harder. Let's talk about that a little bit. Another example, what happens if it's been raining and the sun comes out? The first thing that happens is that the puddles dry up, and then the temperature goes up. The temperature, the water can keep things cool, and it works in the summertime if you use a hose on your body, on your house, for instance. So evaporation is a very important process. The evidence for the reality of climate change, there's a lot of pictures like this. These may be a little bit dated now, but they show some of the changes in glaciers. And glaciers, most places around the world are retreating. There's a few odd ones that are going in the other direction. Usually that's because there's two that are right adjacent to one another, and the flow is just going down one glacier instead of the other. Something like that. But glaciers are generally retreating. The Arctic sea ice is decreasing, and snow cover as a whole tends to be decreasing. This is the record in September when the minimum occurs, and the lowest value occurred in 2012. And you can see overall there's been about a 40% decrease in the summertime, the late summer Arctic sea ice extent. And there's a map there showing what the average used to be back in the 1970s versus 2012. And so sometime around 2030 or 2030s, it's likely that the North Pole will not have summer sea ice, and there will be ships sailing through the Arctic instead of going around through Panama. This is our record that is relatively recent. This was published not very long ago, of the ocean heat content. And this is now going down to 2,000 meters. We've been able to take it back to 1960, but the values are not as good back in time. And we've got some sort of an error bar on here, which is the pink curve. And since 2005, there's an army of autonomous floats called Argo floats that are in the ocean. And there's about 3,700 of these now populating the ocean and making measurements. They reside at about 1 kilometer depth. They go down to 2 kilometers depth, and then they pop up to the surface, and they use a bladder, which is inflatable, and they fill it up with either salt water if it wants to sink, or they pump it dry, and it goes up to the surface. And as it does, it makes temperature and salinity measurements. And then there's a mast, which is an aerial that telemeters the information to ground-based stations, and all of this is compiled, and we have measurements now over the global ocean telling us exactly what's going on. But the record doesn't go back as far in time as we would like. And so I've plotted also on here the carbon dioxide increases. So this is this memory of the warming that has occurred. The ocean heat content is increasing and continues to do so. And so one of the consequences of this, as I mentioned before, is that sea level is rising. This is the estimate of sea level rise going back in time, but the record isn't very good prior to about 1992 because it's based upon individual islands and coastal sites, and then you don't know whether the land's going up or down, and all you've got is the relative sea level. But this is what the estimate looks like. What we do have, though, is the record from 1992 when an altimeter was launched into space, a joint French-US mission, and it's making measurements globally of the ocean to millimeter accuracy once about every 16 days, which are the dots on here. And then there's the overall curve in black and the overall trend. You can see its sea level is rising at a rate of 3.4 millimeters per year. And on the right-hand side here, I've got a scale in inches, so it's gone up about 3¼ inches since 1993. Sea level's gone up globally. Globally, that's a huge amount of water. There are some dips in here. There's an interesting dip in 2011, which was a big so-called La Nina event. There was a tremendous amount of rainfall on Australia. Australia doesn't have a riverine system, so it doesn't run back into the ocean. And as a result, it actually took about 5 millimeters of water out of the ocean, the global ocean, and dropped the sea level back down, but then it came back again. And the high peaks on here in 2015-16 and in 1997-98 are El Nino events. And so that's when there's more drought over land and more rain over the ocean. And so some of these fluctuations, we know what they are, but the overall trend is very much related to both the combination of the ocean heat content increasing and the melting of land ice. So this is one number, one fact that there'll be a test on this later, all right? 4% per degree Fahrenheit or 7% per degree Celsius. Warmer air holds more moisture, and this has consequences. And it's a percent. It's not an absolute value. There's a rule that goes along with this. It's called the Clausius-Clapeyron equation. You can look it up, Google it. So if we have global warming, there's more heat, there's more drying in particular. Think about if you've got a dryer at home, you want to dry the clothes. It works a lot better if the heat is on, but it's not actually the heat that causes the drying. It's the same thing if you have a hairdryer. It's not the heat that's coming out of that hairdryer that causes your hair to dry. It's the fact that the air is warmer and it sucks the moisture out of your hair or out of the clothes. And this means that the evaporation increases. And so this has some consequences. So in places where it's dry, where there's a drought, say for natural reasons, the drought sets in quicker. It's more intense. The risk of wildfire goes up. But in places where it's raining, there's more moisture in the atmosphere. And so it rains harder. And so this is my little attempt at animated graphics. We have a parcel of air here, and let's see, as this air gets warmed up, it begins to rise, and as it rises, it expands because the pressure is lower, there's less air above it. And so here it is rising up, and it starts to rain because it cools, and wow, some lightning, and it rains like hell. All right, so that's my little cartoon with regard to precipitation. And so here's a thunderstorm out on the plains, and so it's occurring now in an environment that is warmer and moister than it used to be. But most of the rainfall that we get doesn't come from evaporation immediately underneath, or even in the immediate vicinity. It actually comes from quite some distance away, and the general rule of thumb is about 4 times the distance. If you've got precipitation occurring over, well, let's say 1 mile for a thunderstorm, the moisture that flows into that storm is coming from 4 miles away on average. And for a hurricane, 250 miles is the radius of a hurricane that you can see, but the moisture flows in from 1,000 miles away. And for a big East Coast cyclone, the moisture is flowing into that storm out of the Gulf of Mexico and out of the subtropical Atlantic. And so the low-level winds bring the moisture in from afar. If you're out on the golf course in the summertime, There's some gusty winds going by. What's that? Where are they coming from? You look out, oh, in the distance, there's a thunderstorm over there. That thunderstorm is reaching out and grabbing moisture to bring it in and dump it down. And as a result, because of more moisture in the environment, it rains harder. And so that means heavier rains. And there's very good evidence that this is actually happening. I thought I should talk about mountains and climate change. Here's a nice picture up in the Rockies. And so with climate change, we certainly expect we will still have winter. There will still be snowfall, and the strong seasons will continue. But there's a Goldilocks effect for snow. If it gets too warm, it turns to rain, above about 35 degrees Fahrenheit. If it gets too cold, the air gets freeze-dried. And remember, 1% per degree, 4% per degree Fahrenheit. So if you're at 20 degrees instead of 30 degrees, that's 10 degrees, 40% less moisture in the air. And of course, as you know, if it's 20 degrees and it's snowing, the snow is small. It won't stick together. You can't make snowmen or snowballs. And so there's this expression, it's too cold to snow. And so the greatest amounts of snow occur when the temperatures are about 28 to 32 degrees Fahrenheit. So this is a Goldilocks effect. It just has to be just right. So more snow is actually a result of a warming climate as long as it doesn't get too warm. Now, of course, it does get too warm at the beginning and the end of the snow season. So the snow season is getting a bit shorter. But in the middle of winter, in December and January, we can actually end up getting bigger dumps, bigger snowstorms than we used to, because it's a bit warmer and the air can hold more moisture. And actually, this is what's happening in many places around the Northern Hemisphere. There is an amplification effect, which is related to the same thing that happens in the Arctic, that if you melt snow and ice, that more of the sun's rays then encountering dark ground, and so it warms up the temperatures even more. This is a snow feedback. And so changes in the Rockies and in Colorado are a bit larger than most of the surrounding states as a consequence. So the consequences of this is the potential for more snow in midwinter, but the snow melt occurs sooner, the runoff occurs earlier, and there's less snowpack when we get to the late spring and into the summertime, with prospects for less water in summer. This is something which should be of great concern here in Durango and in other places in Colorado. And there's a greater risk of drought if the weather patterns just happen to be that way inclined. Then you end up with heat waves and wildfires. We'll talk about that a little bit. And there's expansion of pests as a consequence, like the bark beetle. So Senator James Inhofe doesn't understand this, and he had a stunt where he took a snowball saying, oh, look, it snowed a lot in Washington, D.C., there's no global warming. In actual fact, it was an exact sign of exactly what I was saying, that, the conditions were just right for snow to occur. And this was one of these snowstorms, the East Coast snowstorm called Jonas, in January of 2016. This is the panda in the Washington Zoo. And the little girl on the top left is my granddaughter, who lives in Hoboken, New Jersey. The picture of her yard is down the bottom there. So she was frolicking in the snow. This is one of the things. There's no such thing as bad weather. You just got to make the best of it. I mean, sometimes, even in a hurricane. But this is the record I was talking about of the snowpack. And so here you can see that the snowpack has been generally reduced around the Northern Hemisphere from March through to August, with the greatest reduction in June. But there's actually been an increase, especially in November, December, and January. So this is something to think about. This has consequences right here. This is the overall temperature and precipitation records for the contiguous United States, the 48 lower states. And you can see an overall upward trend in temperature. And the trend certainly looks significant there. There are some substantial wiggles on it. I'll point out some of those in a minute. The variations in precipitation, on the other hand, are much bigger relative to the trend, not as significant. But let me make a few comments about this. So firstly, back in the 1930s, there was the period called the Dust Bowl era. This is when it was especially dry in the center part of the country, and many heat waves, and all of the spikes in the heat waves go along with the very, very dry years, the major droughts that occurred at that particular time. I would characterize the precipitation as looking something more like this. There was really no change to speak of until about the 1970s, maybe 1980s. This jag that I've got in here varies a little bit with season, but it's somewhere in there, and then it sort of jumped to a somewhat higher level. So maybe this is climate change related, but maybe it's related to some of these other patterns that I referred to before, the decadal variability that occurs naturally, and we're not entirely sure about that. But there's been, in particular, more precipitation. This is really east of the Rockies since about the 1970s than there was prior to then. And if it went back to the conditions prior to the 1970s, there would be a lot of people in eastern states that would be in serious trouble because they do not look after their water the way we do in general in the West. And so this is 2012. You may remember 2012. This is actually the hottest year for the contiguous United States on record. 2017 didn't quite make it that high. And it was also very dry, but still nowhere near as dry as back in the 1930s, some of these values back in the 1930s. There was a major drought that occurred at that time, and that had some consequences. These are some of the overall changes. This is from the recent climate report that's just come out. This is looking at 1981 to 2015 compared with the first 60 years of the 20th century, or a bit shorter in Alaska, showing the pattern of the overall warming. And in fact, there's not much warming in a part of the southeast, or it indicates that it was, unusually warm there in 1901 to 1960 in part. But it's been warming otherwise most places. And you can see Colorado in there is one of the redder states. It's one of the times that we're a red state. And down below, you've got the precipitation. So there's not much change in the extreme events in the West, and Colorado's been lumped into this. I don't know whether that's quite right. Certainly California is in that category, but the biggest increases have been in the Northeast, but in general in the east of the Rockies, there's been an increase in extreme precipitation events. So one of the fun things we do as climate scientists is this question of attribution of climate change. I'm going to have to speed up a little bit. With climate models, we can sort of play, I've said God here, and we can run climate models with and without climate change. So down the bottom here, there's a whole bunch of climate models that have been run in two different versions. One is called CMIP 3 and one is called CMIP 5. So these are about 10 years apart. And then the observations. And you can see the black is the overall climate observed record, and the models have a lot of natural variability because of El Niños and weather and so on, but they replicate overall the sort of changes that have gone on. But then we can take out the changes in carbon dioxide and the other greenhouse gases in the atmosphere, and also the changes in aerosols, the pollution in the atmosphere. And then you see the version at the top. You can see a couple of sharp zigs down in 1982, which was the El Chichon eruption, and in 1991, which is the Mount Pinatubo eruption. So these are natural events that produced a cooling. But you can see also that there's a separation between the top and the bottom sets of curves somewhere around about the 1970s, thereabouts, and that's opened up over time. And so it's really since about 1975 that global warming is really manifesting itself through the changes in the global mean surface temperature. This was the statement from the National Climate Assessment Report that just came out. This assessment concludes, based upon extensive evidence, that it is extremely likely that human activities, especially emissions of greenhouse gases, are the dominant cause of the observed warming since the mid-20th century. For the warming over the last century, there is no convincing alternative explanation supported by the extent of the observational evidence. And I've got a little graphic on the right there, which is, what do we do about this? There's mitigation, there's adaptation, and the other thing that we need is information, which is what the climate scientists try to do, is to provide the information to guide what we do about these things. So now I'm going to just talk about some extremes that have occurred. I need to speed up just a little, perhaps. Here, I've already indicated that it's not just high temperatures and heat waves and wildfires, but also the changes in the intense precipitation, the longer dry spells, and the changes in intense storms that really matter. And as a result, there are major challenges for water and water managers. So some recent extremes. So I referred before to 2012. This is what it looked like for the calendar year. And there was only a small spot in the Pacific Northwest that was below normal that year. And I don't know whether you remember that year. It was very warm in Colorado up till about July, not quite so much after that time. And so one of the consequences that happened in June and July of that year are these wildfires, the Walden Canyon fire down near Colorado Springs, and the High Park fire up near Fort Collins, and even up above NCAR. Whoops, that didn't work. What? Hang on. There it is. That's actually NCAR, the NCAR Mesa Lab there. And so, something like over 600 houses burned in Colorado at that time. And then a year later, September 2013, we had the major floods along the Front Range. This is Boulder area, some of the flooding that occurred there, and some other examples. And tremendous amounts of moisture and atmospheric rivers sort of came up out of the region, mainly from the west of Mexico, right up into Colorado for about a week's period. Very unusual weather situation, but tremendous amounts of rains that occurred. And in this slide here, I've got some of the records that were broken. The previous record was 4.8 inches, and we had over 9 inches in Colorado, in Boulder at that time. And there were many places that broke all-time records. So moving on to more recent times, 2015-16, what we've seen in this time is really a combination of the El Nino and climate change. And any time that natural variability, El Nino is an example, is going in the same direction as global warming, then things get amplified. And so these are some of the consequences. There were major wildfires in California at that time in summer of 2015, and also in Borneo. This is where the dry area occurs, in Indonesia with El Nino, and also in South Africa, major drought. And then there was the huge fire in Fort McMurray up in Canada, and that was following an 8-month-long drought that had an El Nino component to it. And then there was some recent wildfires. I mean, this is just astonishing. Down in Australia in February of this year, the whole state averaged 111 degrees Fahrenheit, and there was one place, White Cliffs, which had a minimum temperature of 94 degrees. Minimum temperature was 94 degrees Fahrenheit. And then the other side of the coin, there have been floods all around the world in October of 2015 in South Carolina, in Chennai, India, in Missouri, in November, December 2015, in Paraguay, in Houston. Notice, in Houston, in April 2016, they've had 3 500-year floods in Houston prior to this summer. And then Louisiana in August 2016, in California in January, February. So I put this big tree in there, which is no more because of what happened in January, February of this year. And then I mentioned before that there was a record-breaking hurricanes and typhoons in the summer of 2015. that greatly affected the Philippines, China, Taiwan, and Japan. And also in the southern hemisphere, Cyclone Winston went through Fiji in February of 2016. That's a picture of that, the most intense hurricane ever on record recorded in the southern hemisphere. There was a very unusual coastal El Nino event in early this year. In late February, there was major flooding in Chile, and then in Peru in March, and there was this flood of mud. And look at that in the middle of it. There's actually a woman who emerges out of all of that mudslide there in the middle of this mud. And these deluges continued in Colombia into early April this year. And there was also a cow that got caught up in this. And she actually made it out of there. That was incredible. And somewhere here, they show the cow. Where's the cow? There's the cow. Yeah, amazing. So this is the sort of things which are going on. So then last year, in mid-August, there was this tremendous flooding, 30 inches in places, in Louisiana. Many places exceeded what was referred to as a 1,000-year event. And indeed, record-breaking amounts of moisture were recorded in the atmosphere prior to this event. It was later on, Haiti was devastated by Matthew before it made landfall from northern Florida, Georgia, and the Carolinas, again with many places over 30 inches of rain, so-called 1,000-year events. That assumes there's no climate change, and of course there is. And then in the summer, there was a major flooding that occurred in association with the monsoons in southern Asia, in Nepal, in India, in Bangladesh. Over 1,000 people died, and 41 million people were affected by these floods that occurred. And then we have Harvey. So here's some statistics relating to Harvey. A tremendous amount of damage. The forecasts were excellent. Harvey was a big storm. It became a Category 4 storm before it made landfall. And normally these storms peter out when they make landfall within just over a day or so. About 27 hours is their average lifetime over land. And Harvey kept going for 70 hours before it made it back over the Gulf. But it was big enough, it reached out to the Gulf and had these spiral arm bands that were bringing the moisture in off of the Gulf, especially over Houston, and caused tremendous amounts of rainfall. Down the bottom here, I've got our analysis of the Gulf of Mexico, the actual ocean heat content from the top 160 meters. And during the summer, in August, before this event, the ocean heat content was at record high levels. And so this provides tremendous support for the sea surface temperatures that provide the moisture and the fuel for storms like Harvey. And to me, it was absolutely incredible that only 1 in 6 had flood insurance, given that there have been several floods in Houston previously. This is the rainfall, several rainfalls, over 60 inches in a number of places in this area. Some other pictures there. And so one major comment, following Hurricane Ike, which actually claimed 113 lives in Galveston, nearby, Galveston Bay in 2008, there were proposals for flood control projects, establishing decent drainage systems, no more unbridled growth. And Houston residents have voted 3 times not to enact zoning codes. They have no zoning code. There's no restrictions on building codes, on building in floodplains, on having decent drainage systems. And so to me, they've voted to suffer the consequences. With climate change, you either mitigate, you plan for it, you adapt to it, or you suffer the consequences. And these people have voted to suffer the consequences. So then we have Irma. Irma was the longest-lived Category 5 storm on record. It kept moving over very, very warm waters. It devastated a number of islands. It hit Cuba, a glancing blow, and also even hit Puerto Rico, a glancing blow, before it straddled Florida and went all the way up in an unprecedented way, affecting both coasts at the same time. The forecasts were excellent. On the top right is the actual forecast, but there was tremendous devastation, and of course the governor of Florida is a denier of climate change. They have sunny day flooding in Miami on a regular basis, but they don't believe in climate change, and they don't believe in the climate records which show that global sea level is rising. No plans. So once again, they voted to suffer the consequences. So then there was Jose and then Maria, 3 pictures of Maria there, and the devastation that occurred in Puerto Rico, including the banana crop, which was, 85% of their agricultural input, and tremendous damage. This is a nice picture, sort of a before picture, and then this is the after picture. This is the sort of thing that has happened in Puerto Rico. And so here's 1 week later. They don't know exactly how many have died in association with this. There's some counts as high as over 400, but the official count is somewhere in the 40s. But there's a lot of bodies in the morgue that they don't know how to account for them. And all of the damage that has occurred. So I've got a comment, here's the feds, and there's no mobilization. Where's the local kinds of resilient solar power that might have helped out with this? And so in the case of Puerto Rico, they had 3 disasters. Firstly, there was Irma that caught them a glancing blow. Then there was Maria that caught them with a major blow. And then there was Donald. So there was no resilience, and yet there are counterexamples to this. This is some of the commentary on the lack of preparation, in spite of the fact that it's been known for many years that these kind of risks exist and that the hurricanes are getting supersized because of climate change. And so Cuba, it turns out, is an example. Cuba, is not a rich country, but after 2007, they decentralized their electricity, and after Irma, when Irma went through Cuba, their electricity was restored within a week. And so there are ways of doing this, and there are other places, like Taiwan. In 2015, they had 4 typhoons that went through Taiwan, and they've got hardened infrastructure, and it certainly adversely affects them, but they bounce back within a week or 2. There are ways of dealing with this, but it hasn't been done in any of these 3 places. At the same time, in the West, there was a tremendous number of wildfires going on, and tremendous smoke. We had a lot of smoke here in Colorado at this time in early September, and that smoke actually went all the way across to Europe, rather unusual. And then there was these tremendous ravaging of the wine country from the 10th to the 15th of October. I've got some numbers there, something like 7,000 homes destroyed overall. And yet, here we are in Santa Rosa. In 1964, they had a major wildfire come through that region, and they established building codes and fire breaks, a lot of sensible things. And this is Santa Rosa today, because what happened was pressures of people said, oh, look at this nice piece of land here, which was a fire break. Let's build on there, and they did. And so again, to some extent, the lack of adequate planning and building. If you're going to build in a fire break, at least build a concrete structure, for heaven's sakes. People are doing silly things. And so this is a part of the problem, that we're not planning for the consequences. So I'm going to finish just by saying that we have many facts in physical understanding, but the facts are not enough. The role of scientists like me is to lay out the facts as best we can, and the prospects and the consequences, but the decision of what to do is not ours. This is where you guys come into it, and it involves everyone, and it involves politics. And I'll leave it there. Thank you very much. I'm allowed to take a couple of quick questions if there are any quick burning questions. Yes, sir.
Those that don't believe, scientists that don't believe in climate change, what is their main technical?
The main technical argument usually relates to the quality of the data are not good enough, and the natural variability is much larger, and it all can be accounted for by natural variability. And we've done a tremendous amount of modeling of that nature. We look at natural variability and the El Nino phenomenon and other stuff like that, and we can discount that very confidently, as the National Climate Assessment has done. But that's usually what the nature of the argument is. Yes, sir.
Warmer water, can that cause more frequency of El Nino?
The question relates to warm water and the frequency of El Nino. The frequency probably depends mostly on the size of the Pacific Ocean. So under normal conditions or under La Nina conditions, the trade winds are blowing water across the Pacific. The sun is beating down, there's clear skies in the tropics, and the warm water piles up in the western Pacific, over towards the Philippines, towards Indonesia. And the sea level, on average, over that side of the ocean is about 40 inches higher than it is on the eastern side of the ocean. In El Nino, something comes along, a random perturbation, but it only happens about El Ninos occur about every 2 to 7 years, mainly 3 to 5 years, something like that. The heat builds up in the west, and sort of the system says, well, there's too much heat here, I've got to get rid of it, I'm going to have an El Nino event, and some almost random event can happen, and it can trigger it so that the warm water starts to move into the central Pacific. The trade winds relax. That means there's nothing holding the water up there anymore. The warm water sloshes across, brings all of the weather with it to some extent, and the El Nino happens. The heat moves across the Pacific. It then gets put into the atmosphere through evaporation. The ocean cools off. The ocean is cooler at the end of an El Nino, but the extra heat is what gives you a higher global mean surface temperature as a result of that. So that's why 2015 and 16 is the warmest year on record. Why 1998 is the warmest year on record last century. And so then you run out of the heat, and it relaxes back into the La Nina state or relatively normal conditions. At the moment, we're in very, very mild La Nina conditions, but close to normal conditions. And so these are some of the biggest effects in terms of the weather patterns around the world, and it affects Colorado.
Yeah, thank you very much, Kevin. And I think that if we could have more questions now, but if we save these few minutes, we'll have them when the panel discussion is going on, and then we'll have time for that. So let's thank Kevin for his talk. Thank you.